Welcome. In this lecture, we shall be continuing our previous analysis for the microscopic balances. We have learned so far what are the three ways for microscopic balances in the term of the conservation laws, mass balance, energy balance and momentum balance. Now, after we obtain these equations, we should also have some idea that how to go about implementing these balances in a real life situation. So, in this case we have to follow certain procedure in a step by step manner so that we can arrive at the right equation which represents the particular process under study, and these equations it may be single equation or it may be multiple equations depending on the situation, and these equations are also called the model equations. So, in this lecture we shall be studying this following, that to procedure to make the macroscopic balances for a given system, and whenever we are making some balances to solve the problem, we have to also prescribe some initial conditions, some boundary conditions, because any kind of problem you will find that will have some starting point, and we generally like to trace that how that particular process is progressing with time and what are the changes happening in the process. And another thing is this, what are the conditions which are there at the boundaries of the particular system, because that boundary conditions would dictate the internal features of a process. For example, suppose there are two walls, and these two walls are you can say that these two walls are enclosing a certain room. Okay. Now, you can see that depending on the temperatures at the two walls, the room temperature will be decided. That means, for the wall temperatures are the boundary conditions, and they are dictating the inside condition of the room, and all these things are taken care of whenever you are designing any kind of, say, air conditioner. You have to consider all the conditions at the outside the room, and accordingly you decide that what kind of air conditioner you will select. So, similar kinds of example you will find that in our nature, that wherever we are finding that the conditions at the boundaries are dictating the features within a particular system. Okay? And that is why it is very important for us to judiciously select the boundary conditions. Wrong boundary conditions will lead to wrong interpretations of the realities. Then comes the non-dimensionalization. This particular thing pertains to the solution of the equations, that the microscopic balance equations. You will find that why we need to non-dimensionalize them, so that we can make the solutions more general, and at sometimes we make the solutions easier to handle. So, we need this particular step. And lastly, the modeling assumptions, because even though all the microscopic balances which have been derived and shown to you are in three-dimensional unsteady state, but many situations arise where you find this we need not solve this whole three-dimensional and unsteady state solution. Sometimes we are talking about steady state, and sometimes the process is such that the variation of the particular scalar field in any particular direction may be neglected. In that way, we can reduce the dimensionality of the problem, and it may so happen that we can reduce the three-dimension problem to a simple one dimension, or even if we assume a steady state, we find that that kind of a unsteady state three-dimensional equation may be reduced to a single or a multiple number of ordinary differential equations, and this kind of assumptions lead to a more approachable solution, more practical solutions of these various processes. So, what kind of assumptions we should make, and under what basis, some basic ideas will be given to you, and you will find that in actual life there will be many instances where you have to you have this whatever I am going to teach you, that may form some basis to you to decide that how to tackle the real life problems. Now let us come to the procedure. Okay. So when as we have said earlier also that whenever we are going to analyze a particular system, we first need to figure out that what is the area or the domain which is going to be studied. So we are not going to study everything. We fix a particular domain and we focus our attention on that particular domain and write all the balance equations as per that domain. So what we call this, first we have to select a control volume which should be representative of the actual system. It should not be that the control volume does not represent the system. The whatever is happening in the actual system, the control volume you can say is just a smaller way or miniaturization of the whole space. So in a space we are selecting a and a subspace with the whatever is happening in the whole space will also be seen within that subspace. So that is why we are saying that the control volume choice has to be made very discreetly. Now this control volume should be infinitesimally small. So that means it should have the dimensions of the control volume should be much less compared to the dimension of the whole system, because in the microscopic balance we are trying to figure out the distribution of particular scalar field within the system. Okay, that means we want to find out the profile of the scalar fields like temperature profile, the concentration profile, the velocity profile, etc. So for that we have to go as much as possible point by point, but in practicality, in reality, the point we cannot make a point balance. Okay, so we always choose a small domain which will be having enough space so that we can make the balances, but it should have a dimension which is much smaller than the dimension of the whole system so that we can make the appropriate balances. So this particular control volume is sometimes called the shell. So many times you will hear in the literature the shell balance. So whenever you are encountered this word shell balance, it basically means that you are taking a small control volume and over which you are going to make all the balance equations. Now whenever you choose a control volume, because we are interested to find the profile, that means that we want to know the variation of particular scalar field point by point, location by location. Now you see that whenever we are choosing a control volume, small control volume, if we say that we may question that within the control volume there could be a distribution. Yeah, it is possible, but point is this, the way we are directed to put the control volume, we say that it should be much smaller. It means what? That within the control volume we assume there is a proper distribution or uniform distribution of any of the properties. And you will find that as you found in the derivation of the microscopic balances, there also we started with a control volume. Say for example, in Cartesian coordinate, the control volume has a volume of delta x, delta y, delta z, and this delta x, delta y, delta z were having finite dimensions. But when we ultimately derived the balance equations, what we did, we put these delta x, delta y, delta z tending to 0. That means we are making them very, very small. Okay? So when you make them very, very small, so it is assumed that the particular scalar field will be having a same value over the entire control volume. That means each control volume is taken to be a well mixed system, and then when we take the limit of the delta x, delta y, delta z to 0, we are kind of reaching a point location. Okay? That is how we are going to find out the profile of the scalar field. Now once you make the profile of the scalar in that particular control volume, whatever we have learnt earlier also in the macroscopic balances, the similar kind of theories will also be applicable for the microscopic domain. Now after that we need to define some local coordinate system, and as I told you in my earlier lecture that we derived the microscopic balance equations for different types of coordinate systems. And as I told you earlier that the proper choice of the coordinate system eases the solution of the particular balance equation or equations. So it is very, very essential for us to choose the proper coordinate system. So as we have seen that we have three types of coordinate systems. One is the Cartesian or rectangular, in which we represent in terms of x, y, z. And then we have the cylindrical coordinates, which is represented by r, theta and z, and spherical coordinate, that is represented by r, theta and phi. So all these things are known to us, and coordinate system should be chosen as per the geometry of the system. For example, if we have a cylindrical vessel, the first choice could be that we go with a cylindrical coordinate. But again you will find, when you choose a cylindrical coordinate, with some assumptions you see that the particular coordinate system may get reduced to a rectangular system. That may happen. Okay. But the first choice would be that if the system is cylindrical, say for example we have a reactor, which is a cylindrical column. So for that we may choose at the first time that we choose a cylindrical coordinate system. Okay. So in that case we may choose rectangular, but you will find the manipulations of the things will be such that the geometry of this particular cylinder will make the choice of the rectangular coordinate systems a bit more involved. Okay. So in that way you can see that the geometry of the particular system at hand will be dictating the choice of the particular coordinate system. And then once we do all this, then we go to write the conservation equations. And this is the general conservation equation, that rate of change of any quantity is equal to flow in through the shell boundary, then minus flow out through the same shell boundary, plus some net generation and minus some net consumption. So this is what we have seen earlier. And this particular conservation equation should be kind of remembered, because even if you are forgetting something here and there during your solution, if you remember this basic theory concept, perhaps you can derive many of the equations right on the spot. Then after selecting the coordinate system, make the relevant modeling assumptions, and I will talk about the assumptions later on. And then after, model equations are based on some conservation laws. Now that is not enough, you will find, and we have seen that also when we were doing the macroscopic balances. In that we found that even after writing the model equations, there were some parameters, they were not coming automatically from the balance equation. For example, the density, for example the specific heat, then for example the heat transfer coefficient. So these parameters are not coming automatically, naturally from the model equations. So to estimate these values, again we need some other equations in terms of some correlations, in terms of some tabular data. So all these things come, we call that constitutive relations. So we need the constitutive relations after we set up the balance equations. From that we figure out which are the parameters which need to be estimated to solve the balance equations. So we need to find out the appropriate constitutive relations, that for example we find enthalpy, heat and mass transfer rates, etc. Okay. Now then we have to, after getting the model equation, then the constitutive relation, now before we solve, now we have to prescribe the initial conditions and the boundary conditions. Initial condition means that the state of the process at a given time is prescribed, okay, and that time is generally taken to be 0. There is no 0 time as such, but whatever the starting point is taken to be 0, and then we progress with time. And then boundary conditions, as I told you, that at the boundary of that particular domain of study, what are the various conditions, and I will talk more about the different types of boundary conditions possible for a process system. So as I told you that initial conditions are prescribed for time dependent variable at a specific time, typically t equal to 0, for the whole region of interest. That means the initial condition will be applicable both for the boundary as well as within the system. Okay. And then we have boundary conditions which are prescribed throughout the boundary of the system only, and again these are for all the time. Okay. So, this is the difference between this initial condition and the boundary condition. And sometimes you will find that even though I am telling you that initial condition is for say time, but many a times even in space we find that the spatial coordinate varies like time. For example, you have a steady state problem and one dimensional problem. In that case, you see that suppose you are going from your home to say your college. Okay. Now, you see that suppose you have a one dimensional movement. Okay. You are not going anywhere, one dimensional movement. I can approximate your movement from your home to college as one dimensional system, and suppose it is steady state, that means you are going at constant speed. Okay. Now, you see that the starting point is your home and the ending point is your college. Now, in that case what you find, college or office it could be. Now, you find that when you write the balance equation for this, it may reduce to only a one single spatial direction. So, this will give you an ODE, ordinary differential equation. And when you want to say you get something like say any kind of what do you call it, you want to know the speed, etc. in one dimension, you can write the equation. And then you find that when you put this, you find that the particular space, like if the space is given by say x is direction of your movement, then this particular x may be, suppose you are measuring the temperature along your route. Okay. Now, this temperature variation along your route is one dimensional. Okay. And then you find that you are getting some equation which is one dimensional, and in that case you find that you start the temperature measurement at your home, and then perhaps you are measuring temperature along your route. So, the first temperature which you are prescribing at your home is the initial condition. Now, you see even though physically it is a spatial dimension, but mathematically you find this becomes like an initial condition. Okay. So, mathematically it is different, mathematically it is like an initial condition, even though spatially it is a boundary condition. So, you start like this, that is as if you are replacing time by x. Okay. So, you put at x equal to 0, temperature is this. So, you understand that many times the spatial coordinate mathematically behave like a temporal coordinate, but in reality is not so. Okay. So, that is why you will see that as you go along doing this kind of modeling, you will find that many situations arise. Okay. Then what happens by this kind of mathematical interpretations, you find that the solution procedure becomes quite generalized. You do not have to invent different procedures for different boundary type condition, initial type condition, because mathematically does not matter. Okay. We look at the type of the equation after writing the balance equation, that will decide solution procedure. Okay. So, that is what I wanted to tell you about the initial condition and boundary condition. You should not be thinking that initial condition must be having time in it. It may have some space in it also, mathematically, not physically. Okay. When boundary conditions are specified at less than 3 coordinate directions, then we can say that we have some semi-infinite multidimensional system. Many a times we neglect the boundary effect. Okay. Maybe if the boundary is too far off, we can say that effect is not felt within the system, the core of the system. Okay. Then in that case what happens? We can say that as if it is independent of the boundary conditions. It happens in many systems. As we go along, we will find many systems. I will give example to you to tell you that how a actual 3-dimensional system may be reduced by considering an infinite dimension in one particular direction and reduce its spatial coordinates. Okay. So, these are what we call the semi-infinite. It is not infinite, semi-infinite, because we are still retaining the variation in 1 or 2 directions. So, we are not trying to solve for all the 3 directions. And then whenever we are talking of these boundary conditions, initial conditions, how do we decide? that how many numbers of initial conditions is to be provided, how many boundary conditions are needed. So this is very simple for you to judge. You will see that number of independent initial or boundary conditions is equal to order to which the partial derivative is raised. Now order and degree perhaps you know. Okay, let me just recapitulate for you that order. Suppose I have a something like d dou y by dou x plus ay equal to say c. Okay, so this is a first order equation. Okay, so you see that the highest derivative we are doing. Okay, now suppose I write the same equation like this, dou y by dou x whole square plus ay is equal to c. Now in this case the difference is what? The order still remains 1, but the degree is now 2. Here the degree is 1, here the degree is, so this is order 1 and degree 1, and here order is 1 and degree is 2. Okay, so this is the difference between the order and degree. So similarly, if you have, so let us write a second order equation. Now let us write another equation which is of say order 2. Okay, so let us see like this, dou 2y by dou x square, say some dou y by dou x plus say by equal to c. Now in this case you just see that what is the highest degree of the derivative. Here you see the highest degree is 2. So this order is 2. Okay. Now if I say what is the degree of this equation, now again you have to see that this degree is the power to which this particular equation has the highest power is there. Highest power is again here 1. Okay, so degree is 1. Okay, so I hope that you can understand that how we decide the order of an equation and degree of an equation. Okay, so suppose this goes to a square, so order still remains the 2. Okay, so this you should be very careful. So here what we are saying about this, that the number of independent initial or boundary conditions. This word is very important, that they should be independent. There should not be dependency of the initial and boundary condition each other. If they are dependent, then that means we are over specifying the things. Okay, so we should not over specify anything. So there will be independent initial or boundary conditions equal to order to which the partial derivative is raised. For example, like if we have a single order, that means only one condition is to be specified. For double derivative, we have to specify 2 conditions, and generally you will find that the derivative in the time direction is generally 1. Sometimes we get 2, but generally it is 1. But for the space derivative, you will find that we get both type of things, whether we get both single derivative as well as double derivative. Single derivatives are generally associated with some convective terms, and double derivative are associated with the diffusive terms. Okay. Now we come to the boundary conditions. They, as I told you, that they represent the conditions at the boundaries of the domain of study, and all boundaries need not have physical existence. This is very important. As I was telling you that boundary is from the mathematical point of view. Okay. Now for example, let us talk of a sphere. Let us talk of a sphere. Suppose this has this center, and suppose the radius is say capital R. Okay, and let us say that any radial position is given by say small r. So that means R will be varying between, say, this is, suppose this is the 0 origin, okay, between 0 and r. So, suppose we are writing some balance equations, maybe in terms of concentration, velocity or temperature. So, what we generally do, that if we find that we have a second order equation, we find that we have to specify the value of the, say this is the phi is the particular property for which we are solving it. Okay. Now, this phi we has to be specified for boundary condition, you have to specify at 2, say R1 and R2, okay, at 2 points. Now, say R1 I choose because I have to solve within the whole spherical domain. So, I will choose this R1 equal to, say, 0, okay, and this R2 I select as the this particular periphery of the sphere. So, I put this R2 equal to R. Now, you see that when I talk of R2 equal to R, it means what? That this is a physical boundary, I can see that. Okay. But when I talk of R equal to 0, there is no physical boundary, there is no boundary here, it is just a starting point we have taken. So, that means what? The boundary conditions need not have any physical existence, they are just a kind of, you can say, some mathematical way of representation of the particular process, where starting point and ending point. So, that is what it said, that all the boundaries need not have physical existence. Okay. So, this is what I have shown you by this particular example. Now, only one boundary condition should be set for one boundary region, that is, there should not be multiple boundary conditions for the same domain, otherwise it will, there will be kind of a, could be a clash, because at a given particular location we have only one and one condition, it cannot have multiple conditions at one location. For example, if you are saying that there is a, suppose you are putting a pan with some kind of, say, water or milk on the oven. Now, you see that that when you are putting on the oven and you are burning this thing, then what happens? The liquid inside the pan will start get heated up. Now, boundary condition could be that what is the temperature maybe at the bottom of the pan, or maybe how much heat flux is being inputted through this bottom of the particular pan. Now, you cannot prescribe both the heat flux as well as the temperature at the bottom, because if you keep one fixed, other will have to vary to keep the first one fixed. So, if you want to keep the heat flux first, the temperature has to vary, and vice versa. So, you see that multiplicity of the boundary conditions is not permissible to define any kind of physical problem. So, you have to see that what kind of boundary conditions you should have. And now, we see that there are various kind of boundary conditions in various systems, but all these boundary conditions again may be classified into 3 basic types, and here I am showing the 3 basic types of boundary condition. First, what we call the type 1 or Dirichlet type. So, these are the names of the scientists who proposed this kind of boundary conditions. Okay. So, type 1 is Dirichlet type, and this is when we are prescribing the value of the functions. That means what? That suppose, as I told you, that in the pan you are heating some liquid. So, you prescribe the temperature at the bottom of the pan. So, that we call the boundary condition of type 1, or many times we call them Dirichlet condition. Okay. So, this way you can also figure out that suppose you are starting a car, okay, from rest, we say it is the boundary condition is that we can say that it is rest means it is type 1, that means we are prescribing the value as of the velocity of the particular car. Now, please understand that whenever we are putting the value immaterial of the time or boundary conditions, it does not matter that whenever we are putting the value specified value, we are calling it type 1. Okay. We are not giving any kind of derivative or other thing. Now, when we go to type 2 or what we call Neumann condition, here we are putting some kind of normal derivative, for example flux. So, you are saying that what is the Say you are having a pipeline through which some liquid is flowing or gas is flowing. You are saying that what is the mass flow rate per unit area at the inlet of the pipe. So, that is a flux. So, in this, when you are describing the flux, that becomes the second type, type 2 boundary conditions. Okay, with so any kind of acceleration you want to propose. So, that will be a flux boundary condition. That means any kind of derivative when you are proposing. Now, when you understand this, when you propose a velocity, velocity is a derivative if you are trying to find out the location. Okay. Now, if you prescribe the acceleration, that becomes the derivative if you are trying to find out the velocity. Okay. So, you have to understand this, that whenever you are prescribing this, you cannot say that, see, if you are trying to find out the velocity profile through a pipeline, if you provide velocity, then it is, even though velocity is dx by dt, it should not be taken as the type 2 boundary condition. It should be taken as type 1 boundary condition. But if you are prescribing the acceleration, then it should be treated as type 2 boundary condition, not type 1 boundary condition. That means the scalar field for which you are solving the particular balance equation, that value should be prescribed at the boundary to qualify as type 1, and that derivative should be considered if for type 2. Okay? Not any other variable which may be derived or derived from that particular actual variable, or maybe that particular variable which you are solving for can be obtained from other variable. Okay, not that way. Okay, you have to consider the particular variable which we are solving for. Okay, that's very important for us to know. And then is type 3 boundary conditions. It means this type 3 is what we call Robin's boundary condition or mixed boundary condition. In mixed boundary condition, you have both the a kind of mixture of both the type 1 and type 2. Okay. So, here this will be leading us to some algebraic differential equation, and for infinitely large boundaries, the size is set at large value, and we may set all Dirichlet or all Neumann as 0. So, this is another thing, that whenever you have infinite, as I was telling you, that if you have semi-infinite domain, so we may, that means the size is taken to be too large, because infinite, how to represent infinite? There is no way to represent infinite in means in kind of when you are going to make some kind of coding or something. So, you put a large value compared to the actual domain of your study, the dimension of domain. Okay. So, in that case, what you do, either you put all the Neumann conditions to be 0, that means you say that velocity profile for that, you say that dou v by dou x or dou v by dou y or dou v by dou z to be equal to 0 at the boundary. Okay. Or you say that the velocities are some constant. Okay. And it is not that you have to prescribe only first order derivative, you may prescribe second order also. That means you can put dou 2 v by dou x square as 0 or dou 2 t by dou z square as 0. Okay. So, it has to be some derivative. So, this kind of things are also done mathematically to solve these domains whenever we have some infinitely large boundaries. And here I have shown that if I take a 2-dimensional case, here I have shown that how we apply these boundary conditions. 2-dimensional case we have. So, you see that we have taken all this with different kind of boundaries. This sigma 1 is one boundary, sigma 2 is one boundary, and sigma 3 is another boundary, and D is the domain of interest of study. Okay. Now, you see, when we talk of type 1 or Dirichlet condition, what we mean, we shall be prescribing, say we are solving for some variable phi, maybe temperature, maybe velocity, maybe something else. So, we are prescribing the phi value as a function of x y, okay, on the sigma 1. Okay. So, here we are prescribing this whole domain, we are prescribing the value of the phi. That means, it need not be a constant but specified. Okay. It should not have derivative. Okay. Similar thing goes with the initial conditions also. In initial condition also, you should not, when we say specified, it should not be taken as constant value, it should be taken as a variable, but in say in case of initial condition, the initial condition may be a function of space. Okay. So, it should not, it is not a constant. Similarly, when we say this, we say it may be function of this x y, but should not be having any derivative. In the second boundary thing, if you talk of second this type 2, we can talk of this, that dou phi by dou n equal to some function on sigma 2. So, in this particular domain we are putting a type 2 kind of boundary condition. And next is the type 3. Suppose in this sigma 3, what we are saying, you can see now this particular equation. Here we have this type 1 type and this is type 2 type, and again we are having this a combined boundary condition. So, this is a differential algebraic equation, okay, and we say that alpha x phi and beta x phi are more than 0 and this x phi belong to this particular domain. That means, we are solving for x phi not outside domain, but within this particular domain. That means, we always this particular thing means, it means that we have to always travel inside, okay, from any boundary we go, we have to travel inside. So, we cannot travel outside, this is not permissible, okay, that is the meaning of this particular thing, that x phi must belong to the domain of our study. Okay. So, these are just few references in which you can find a very good exposition about the concepts and topics I have covered in this lecture, and we shall be continuing this lecture for some more on the procedure of these balance equations. Thank you.